So I just wanted to reward the brave of you who braved the weather and came here, okay, right, instead of staying home, all right? So these folks who stayed at home will never know what we talked about, all right? So, okay. So, as I was saying, for the most part, problems in the world are difficult and complete. In this class, we learned the few tricks we know, and they work for some problems, all right? And now we're going to talk about the last one, linear programming, all right? And then there is a sprinkling of spots of light, which are the problems that can be solved by dynamic programming, okay? It's a method that works in many contexts, all right? Very general method, works in many contexts. Now we're going to talk about LP. What's my point? My point is the following, that the situation is a little less bleak than this because of the following, that these light spots, they have an environment which they attract. In other words, there are some problems in the periphery which can be solved using these methods, okay? And linear programming is famous because it has a very large periphery, okay? There are many problems that can be solved using linear programming. My point is that these arrows here are called reductions, okay? Extremely important concept, okay? Reduction is a trick that allows us to multiply our possibilities, okay? To multiply the problems that we can solve, all right? For every algorithm we find, for every problem we manage to solve, there are many other problems that reduce to it, okay? That can be solved by changing the problem so that it can be solved by the other algorithm we discovered, okay? I don't know if you know the old joke, okay? That there is an oral exam in some university, and it's about physics or thermodynamics or something, okay? And there are two examinees in the room, a physicist and a computer scientist, okay? So the professor asks first the physicist. Imagine that you have a stove which is off and a pot that has no water in it. How would you produce boiling water? And the physicist thinks and says, well, I will fill the pot with water, I will put it on the stove, I will turn it on, and this way I'm going to have eventually boiling water. So the guy gets off, gets an A+, all right? Then now is the turn of the computer scientist, and the professor of physics says, he's a little, he doesn't want to give the computer scientist a hard time. So he says, all right, imagine that you have a pot full of water and a stove that is on. How would you produce boiling water? And the guy says, well, I will empty the pot, I will turn the stove off, and so I have reduced my problem to the problem that my colleague solved before, okay? So that's what the reductions are, okay? So, we know how to solve a problem, and so we take a new problem and you transform it in a way that can be solved, fits the specs of the problem that we have solved, okay? Questions? So this is what these other problems are, okay? They cannot be solved. We don't know exactly how to solve them, but we know something better. We know a way to transform them into a problem that we can solve, okay? And if you want to understand what linear programming is, really, it's a problem which is extremely centrally located. It is extremely useful in such a way that many other problems reduce to it, okay? So linear programming owes its centrality in computer science because it's very easy to reduce other problems to it, okay? So it radiates solvability, okay? Many other problems reduced to it. And that's what we're going to talk about. So many of you have seen linear programming, I think from high school even. But let's go through the motions. Let's come up with a little program, okay? Imagine that we want, and I'm not going to bore you with the narrative, with the story. There is a company who has 2 products and wants to maximize x1 plus 6x2. From the second product, it gets 6 times the revenue than from the first product. X1 is the amount of the first product is going to produce per day, let's say. X2 is the amount of progress it's going to produce per day. And 1 and 6 is the revenue in dollars that the company is getting from every such product produced. And it has some production constraints, production, workers. Okay, so this is our linear program. This is called an LLP. What is it? What it asks? It asks you to maximize an objective function, as it's called, okay? The first thing is called an objective function, which is a linear function of the variables, subject to constraints, which here happen to be linear inequalities in the variables, all right? So that's, and typically, we will also require that the variables be non-negative. So you have all seen it, okay? So let's see how to solve it. And there is a neat way to solve it. Basically, graphically. Here is x1, here is x2, here is x1 less than or equal to 200. Here is x2 less than or equal to 300. It means this way and this way. So this means this rectangle. And this is x1 plus x2 less than 400. I guess it's this one. Okay? So all in all said, what we are left with is, and of course we want x1 to be positive and x2 to be positive. So all in all possible, feasible production plans, this is called the feasible region. This is called the objective, okay? The first one. These are called the constraints. So the constraints define for us a region in the plane. Always has to be a convex polygon. Why a convex polygon? Because it is the intersection of half spaces, right? In 2 dimensions, it's going to be a convex polygon. In 3 dimensions, it's going to be a convex polyhedron. In 4 dimensions, I've never been there. I don't know. Okay, you know. So, okay. So, and now you have something else. You have this x1 plus 6x2. In order to make sense of a particular sort of form like that, like a linear form, the best thing is to make it equal to something. Equal to what? Let's say equal to 2100, okay? To 2800, to whatever, 1400. Okay? In which case, 1200. What's the answer here? I forget. Yeah, let's say 1200. In which case, x1 will be over here, and x2 will be here, and basically, this will be our equation, right? Yeah. I just made up a number. Yeah. So this is the equation x1 plus 6x2 equals 1200, right? And now you know what it is. If I put this into, I don't know, 1500, it will be a little higher, right? Everybody sees that? 1300, a little higher. So the point is, the point of the exercise called linear programming in 2 dimensions, okay? In the easy case of 2 dimensions, which all of you probably have seen in high school, is a way to push this line upwards. Why upwards? Because it's a max problem. Until it's about to leave the feasible region, okay? To find the upwardmost point where this line can touch the feasible region kept parallel to itself, okay? So that's what we have to do. And we all know what it is. It's this point here, right? Okay? Nothing mysterious. And it turns out that the best answer is, I don't know, x1 equals 100, x2 equals 300, and the objective, the first guy, is 1900. Okay, so the best thing to do is produce 300 units of the lucrative second product, 100 units of the first product, and this way the company will make 1900 per day. All right? Everybody with me? Okay, cool. Now, I want to be a little more systematic about finding the optimum. I'll give you a preview of a very clever algorithm that we have in order to find the optimum. That's called the simplex algorithm. The simplex algorithm is a simple algorithm, okay? So it's a very naive algorithm, and it does the following obvious thing. It starts, first of all, we have to realize one thing first, that the solution we seek is going to sit at the vertex of the polygon, right? Everybody believes that. That if you push a line until it leaves a polygon, the point where it's going to leave it is a vertex, okay? Maybe it's an edge, but an edge has a vertex, so it's a vertex. Okay, so we are looking for the best vertex. This is an immense progress, okay? Instead of looking any point inside the polygon or at its boundary, we are looking at one of these 5 vertices, okay? Of course, it's not going to be that simple, because in more complicated problems, the number of vertices will be exponential, and so we cannot afford to do that, all right? But the point is that simplex does something clever to find this vertex, and does the following. It says, let's start, it's going to be a vertex, right? So let's start at some vertex. And usually it picks a vertex which is very accessible, all right? In this case, the vertex where we don't produce anything. All right? And then it looks around and says, from this vertex, I can see 2 more vertices. Is any one of them better in terms of revenue than this vertex? Better be, right? This vertex has revenue 0, all right? And now it says, yeah, if I go here, I'll make 200 bucks. Here is 0 bucks. So yes, so in a sort of a way that it just looks at its neighborhood and says, okay, that vertex is better than me. Let's go there. There are many. This is not exactly greedy. It's something else. It's called local search, right? I mean, you look around, you try to find, to improve by looking only at a few things around you, all right? You improve, then you improve again, then you improve again, right? That's called local search. It's a nice, we'll come back to that later. So we're in the local search mentality. Here we are trying to find a neighbor which is even better. And you can find that. Here it is. This one, I guess, has 1,400 revenue. Then we go there. And to make a long story short, this way you are going to discover this vertex. All right, so what I'm telling you is that in principle, there is a very naive way of finding the best vertex. And the idea is, okay, local search is a generic genre of algorithm, right? What it does is it says, I start with some solution. I look at solutions that are close to the present solution. And if I find any solution which is better than me, I go there. I adopt it. OK? And then from there, I repeat the same thing. And when I am at a solution which I cannot improve by going to any of its neighbors, I'm at a local optimum. OK? That's how it's called. Local optimum is the result that local search gives us. And the point here is that we are in a happy situation in which the local optimum is always the global optimum, because it stands to reason, right, that if you look around you and you don't see anybody who's better than you, you are at the best solution. Intuitively, it's clear. There is some math involved there. OK? Any questions? So this is linear programming, but sort of a very easy case. All right, let's go to more. Imagine that we have. Let's add more. Okay. Imagine that this company has an even more lucrative product, a third product, and now it's x1 plus x2 plus x3 less than or equal to 400. And you also have another constraint that says that whatever, x2 plus 3x3 less than or equal to 600. OK, so now we have a new linear program, which is essentially the same one, except that now the company has three alternatives, three options. And there is nothing changes. We can still find a three-dimensional feasible region. And in this case, it's this. Notice this is this guy, OK? Because in the x1, x2 plane, the situation will still be the same. OK? But now things are a little more complicated. OK? That's what's going to be the solution, the feasible solution, because you see, the first inequality is this side. The second inequality is this side. The third inequality, what am I doing here? The third inequality is this one. And the fourth inequality, the third inequality is this one. So that's number 1, that's number 2, that's number 3, that's number 4. Where these are the 1, 2, 3, 4 inequalities, OK? That's 4. It turns out that's how it works. And the point is that simplex still works, OK? it would still do the same thing. It would start this way. Then we would go that way. But now instead of heading here, it would head here, and then would head there. And that's the optimum. The optimum is, I guess, x1 is 0, x2 is 300, x4, x2, x3 is 100, and it has 3100, if you can check it. Yeah. 3 times 6 is 18, plus 13, 3100 profit per day. All right, so boring. By introducing a third product, the company can get a lot more money. Okay, sure, fine. So what are my points? My point is one. You can write inequalities and equations and define a linear program. The linear program defines a feasible region, and then you can use a method called simplex, which sounds like a brain-dead method. I mean, what it does, it starts somewhere, and then it tries to improve it by looking around only, okay? The vertices that are visible from the current vertex, okay? Okay. Also, the point I want to tell you is this, that companies usually, they don't have 3 products, they have hundreds of products, all right? I mean, and thousands of constraints of all kinds. And therefore, our geometric intuition is doomed, okay? So, it will not go another step, all right? So that's fine, though, because simplex, as we are going to see, we're going to understand simplex quite thoroughly, can be done algebraically. It doesn't have to look, to eyeball the vertices and move around. It can be done in a very simple algebraic way, and we'll see about that, okay? And I have a different point, okay? And this one is, I think, an amazing fact, and I want you to pay attention, all right? Okay, so pay attention, because it's something really neat is coming. I'm going to prove to you that you cannot do better than 3100. 3100 is indeed the optimum, okay? Here's how I'm going to prove it to you. All right, watch. I'm taking the first equation, x1 less than or equal to 200, okay? Sorry. I'm taking the second equation, x2 less than or equal to 300. The second inequality. I'm taking the third inequality, and I'm taking the fourth inequality, okay? And now I'll multiply this by 4, and I get, I guess, 4x2 plus 12x3 less than or equal to 2400, okay? I forget about this, and I add these two, and here's what I get. I get that x1 plus 1, 2, 6 x2 plus 1 plus 12, 13 x3 less than or equal to 3100, because it's 300 plus 400 plus 2400, 3100. You should be very impressed. You see what I did? I proved to you that the objective function, which is 6x1 plus 6x2 plus x1 plus 6x2 plus 13x3 can never be greater than or equal to 3100 in any region, in any point that satisfies these 3 equations, and the fourth, of course. Sorry? Say again? Yes, yes. So what I did is I multiplied these inequalities by 1, 1, and 4, and 0, and I added them up, nothing else, okay? All right? So here is an amazing fact, that this is not a lucky case. You can always do that in linear programming. Okay? You can always find something called a dual solution. This is what this vector is called, is a dual solution. Okay? And this dual solution will demonstrate to you immediately that this is an optimum, that the optimum we found is an optimum. And the point is, not only that once you solve it, you have this, but this is how you solve it, okay? You cannot solve linear programming without finding this, okay? So that's an amazing fact, all right? I didn't impress everybody, that's okay, yeah.
In other words, you're saying, so if something gets very hugely complicated, all you do is use the algorithm to solve it?
You use simplex to solve it. Simplex does not need geometry. You can do it simplex works in an algebraic way, and simplex gives you, as an extra bonus, this solution here, okay? Which gives you confidence that what you have is indeed the optimum solution. Yeah. Yes, if the question is whether if simplex can ever fail. In many cases it can fail, okay? Imagine that your linear program is maximize x1 plus x2, subject to x1 that is equal to 3, and that's it, okay? And x1, x2 are greater than or equal to 0. Okay? In other words, you can give it meaningless problems, okay? This is meaningless because it has no upper bound. You can make it as big as you want, okay? Make x2, and if, 100, 1,000, million, anything, trillion, anything you want, it's fine, okay? So simplex will scream at you, okay? Or you can give it something that the feasible region doesn't exist, okay? So it has been constrained out, okay? It will always be convex. It will always be convex because it's linear inequalities. Okay, linear inequalities will always give you something convex. Everybody understand what convex means? Convex from calculus? Convex means the following. Why is this region convex? Why is this region convex, okay? And this region is not convex. This region is convex because no matter which points you give me, the whole line between them is going to belong to the body. Here I can give you 2 points so that parts of the line between them will not belong to the body. Okay, that's bad. This means it's not convex. This is the convex hull of this region, right? I mean, every region can be closed so that it becomes convex. But as I gave it initially, this region was not convex. And the linear programming has a lot to do with convexity, okay? It exploits convexity. That's why geometrically, in 2 dimensions, it's a convex polygon. In 3 dimensions, it's a convex polyhedron. Yeah? Why is simplex fast? This is something we are going to face when it comes, okay? Right. So in general, it's not. All right? Okay. So what I want to do now is talk about a few examples. Okay, give you a few more examples. So to show you the kind of things that you can do by linear programming. As I promised, linear programming is not so much a very interesting problem to solve by itself, okay? It's interesting only because you can take millions of problems and reduce them to linear programming, okay? So let's do one example that's in the book. And this is both an example and a cautionary tale, all right? So imagine that you are running a business, okay? Very much like this one. except that this time the demand varies, okay? It's a seasonal demand, it varies. So you have for next year, you know the demands for every month, okay? And they vary, they go up and down. And somehow your marketing department is super smart, they have figured out all the demands, all right? In the beginning, you have employees, workers, 30 workers, and each one of them does 20 units per month. So every worker, in other words, you can manufacture, as things stand, 600 units per month. Also, you can have overtime. It costs 80% more to have overtime. In other words, you pay a lot extra your workers to work overtime. And people cannot work more than 30% overtime. Okay? All right. So besides overtime, you can hire or fire people. And this is costly. To hire costs, and to fire costs $400 a worker. And I forgot to tell you, the workers get $2K per month. And also, you can store. And in other words, you can if your January demand and February demand is low, but your March demand is forecast to be high, then you can work a little harder in January and February and store the units you produce. But storage costs, it costs you, let's say, $8 per unit per month. Okay? So the question is, find the company's best production plan. All right? And this is very well suited to be solved by linear programming. First of all, this is what we do in linear programming, you have to remember. Sometimes it's easy, sometimes it's ingenious, it requires cleverness, ingenuity, is to find the variables. What are the variables? What are the x's, okay, that we're going to have? So let's say variables. So that's the first step for setting up a linear program. And xi is the number of units made in month I. Yi is the number of workers at month I, and we know that W1 equals 30. The first month we have 30, and let's assume that only in the beginning of the month you can fire and hire workers. Yi is units made by overtime. Hi and Fi, are the workers hired or fired in the beginning of month I. And Si are the units stored. At the end of month I. Okay? And now we have to write the linear program. First of all, we have to say that xi, wi, yi, fi, hi, si must all be non-negative, okay? These are 72, okay? 6 times 12 inequalities. There are there are applets you can download from the web, and you can type this in, and out comes the solution, right? So that's then you have to say that the number produced at time I is 20 times the workers you have plus the things that are produced over time. These are the amounts produced at these are the amount this is the amount produced at month I. Then what? Wi has to be Wi minus 1 plus Hi minus Fi. Then Si, the things that are stored at the end of period I, is the things that are stored at period I minus 1, plus Xi minus Di minus the demand. Then you want to say that the overtime cannot be more than 6W, because it's 30% of the production capacity of every worker. And basically what you want is you want to satisfy your demand. In some sense, this says it. And then what you want is to minimize the operation costs, all right? And operation costs are the sum over all months of 2,000 times the number of workers you have to pay, plus 320 per hire, plus 420 per firing, plus 8 per unit stored, plus it turns out 180 per unit produced over time. Yeah.
Why exactly is it 6 WI and why exactly is it 180 YI?
Okay. So every worker produces 20 units per month. The 30% of this is 6. Okay? So every worker can produce 6 units per month over time. All right? And it's the same thing. So why 180? Because every unit costs us, every ordinarily produced unit costs us 100. No. So every unit, because every worker gets 2K and is and produces 20, will get costs us 100. Okay, and we know that overtime is 80% more expensive. So that's why the cost per unit over time is 180. Okay, I telescoped a couple of calculations. Okay? What's my point? The point is that a complex production planning process like this can easily be transformed to linear programming. Okay, so linear programming is very well suited to solve any such problem where the equations are linear, okay? All equations and all the things that you want to maximize are linear, all right? And there is a catch, okay? Suppose that you solve this linear program by simplex and tells you that in the beginning of April, you have to fire 8.2 workers, okay? Which is totally possible, okay? I mean, eventually simplex is going to be solving linear equations, and God knows what the results will be, okay? So what I'm saying is that this can be a useful formulation, but the result of it can be useless, okay? Because once you get a number like that, so you say, all right, now what do I do? Do I do 8 or 9? Or maybe both of them will get me very far, and what I need is something else, okay? Who knows, all right? I mean, it's a complicated process. And what do you do now, okay? In some sense, you are stuck, all right? So what is it that I want you to remember from this example? That in linear programming, often you get fractional solutions, fractional answers, okay? For some applications, this can be very bad, okay? This can make the results of linear programming useless. I mean, you cannot implement those, all right? And as a result, you have to come up with new techniques that take a linear program and return to you only integer solutions, okay? And the point is that's a tall order. This is called integer linear programming. Linear programming, we can solve. Integer linear programming is linear programming's evil twin. Okay, so it is much, much, much harder. All right? Integer linear programming is NP complete. Okay? So even though we can use linear programming to find scalar, rational, real solutions to problems, when the application is, or the reduction is such that we require our solutions to be integer, whole numbers, then we have a problem. All right? Then we are faced with a variant of linear programming which is much, much harder. Okay? This, by the way, is a very common phenomenon, all right? That you take a problem that you can solve very well, and then you change something to it. Like you remember, in shortest paths, we said, imagine that you want to find the longest path, okay? Suddenly it becomes NP complete, all right? So, and this is completely in agreement with this bleak picture I painted at the beginning, okay? It means that if you are here, if you know how to know a problem, and you step out in the dark, chances are that you are going to find an NP complete problem, right? Any questions? Okay, so linear programming is extremely useful, many applications. It's no good when the application or the reductions require us to have integer solutions. All right? Okay, so let's talk about another problem that we can solve by linear programming. Imagine the following situation. Okay? So here is a directed graph. It has a source and a sink. The edges have numbers on them. Okay, important difference from what we have seen. The numbers now are not lengths, are not weights, they are something else. What are they? They are capacities, okay? The best way to think of these is as bandwidth in this wire, or if you wish, number of barrels per second that this pipeline can carry, okay? Is it clear? Are we together? So you have this, let's say, network of pipelines, and you are very interested in transporting oil or some other important commodity, liquid commodity, from S to T. And the question is, it's called the max flow problem. Can you guess what we are looking for? We are looking for the maximum amount that you can transport from S to T. Is this clear? So, and the rules are clear, right? I mean, what happens is that at every node, what comes in must come out, okay? Kirchhoff's law of currents, right? And there is no Kirchhoff's law of voltages, all right? That's the only constraints, that what comes in must come out, and just that, and also that no capacity can be exceeded, all right? So I want to ask you, anybody can figure out how much material we can ship from S to T per unit of time? From the longest path problem. I don't see what's the connection. What we want here is to simultaneously fill as many of these pipes as we can. Okay? Yeah. Just 9? I can see that you can get 11 out of here. Can anybody do 10? Everybody understands the problem? Yeah. Tell me. 5 and 5. Okay. Excellent. Right. 5. Right. 5 more. Everybody sees how to do 9? Okay. So, 5 and 5, 3, 2, 2, okay? And now, we do 4, 1, 1, 1, 3, 3. Okay? I can do 9. I pushed 9 out of S, and I was able to dispose of all of them. Okay, so I'm good. 9 is... Here is a lethal trick, okay? You won't believe this. Like in the first problem, okay, the first stupid problem, I can prove to you that you cannot do better than 9. Anybody can see how you can you prove to me? Yeah. Yes. There's an algebraic way, and we'll talk about it. Yes. How common sense? Yes.
You take the line, vertical line down, 9 is the minimum number.
Exactly.
And that's telling that.
Get it? Any flow that goes from S to D has to go through this line. Oh, let's make this 6 then. What do you think? Still, get it? Now, this is 9. 3 plus 2 plus 1 plus 3. Okay? We are doomed. 9. Okay? The amazing thing is that, like over there, this you can always find that. Yeah?
Sorry, I don't think I understand. Why can't you like send 5 and then when that goes down, send 5 more? Like how long do you have to get the shipment?
So basically what we want is to have a steady state operation where every second the same number of barrels of oil is shipped across, okay? So for basic reasons, the capacity of this network is 9, okay? So it cannot do better than 9. That's this cut, okay? So for 2 reasons, this cut and the other cut, you cannot ship more than 9 units of oil. Everybody sees that? Common sense? We'll see that it's also, it's a very strange, you know, there is an amazing story that goes with it that came out recently. I don't know if you probably read it in, it was published in the newspapers. So here's a story that in the 1940s, in the Soviet Union, they had mathematicians look at a network like this, which was the railroad network of the Soviet Union, okay? And basically, they wanted to rebuild after the Second World War, and they wanted to ship. They had a few huge cement factories in the West, okay? And they wanted to ship it throughout the Soviet Union. And they wanted to know how much cement can they ship every day to the vast Soviet Union. All right, everybody understands the problem? It was sort of something like this. It was a problem like this. Instead of one sink, it had many sinks, but never mind, it's the same problem. All right? And the mathematicians of the Soviet Union worked very hard, and they found the optimum solution, okay? And it was a number, okay? So you know that so many trains can go through this vast network of railroad lines. Now, a few years later, the Air Force, the United States Air Force, hired some mathematicians from Rand Corporation and Cornell and asked them the following. They gave them the same network and told them, where do we have to hit this network so that we can completely create a cut, destroy it, okay? And the 2 mathematicians, and it was Ford and Fulkerson, they found the cut, okay? They found this thing, all right? And of course, it was the same value, all right? So in other words, these 2 adversaries together, look it up at Google News, Soviet Railroad Network Max Flow Theorem, okay? So it's a really neat story. These 2 teams of mathematicians, they discovered this beautiful fact that you can solve this problem, and in fact, the solution is the same as if you were looking for the cut, okay, not the maximum flow. All right? And amazingly, the reasons why this theorem exists and why for every network you can find a cut equal to the maximum flow is exactly the same reason why we were able to demonstrate the optimality of this stupid linear program, okay? So, okay. So, all right. Let's go back to square one. We have this problem. How do you want to solve it? How do you think we can solve it? Can be solved by linear programming? How? Okay, excellent. So let's do it. Let's write the linear program. First of all, what do you have to maximize? What are the variables? What are the variables, do you think? Remember, the variables, when you want to set up a linear program, the first thing you have to, and as you will have to do in your homework, the first little problem you have to facing is, what are going to be my variables? What are your variables here? Sorry? Right, so it's what? It's the, sorry? What do you say? For what? For every vertex, okay? That could work, I'm not so sure. For every edge, yes, right. I mean, that's what I was thinking. To say that let F sub SA be the flow that goes here, right? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9 variables. So it is flow SA, flow SB, etc., flow CT, DT. Okay? What do you want to maximize? Want to minimize or maximize? Maximize. What do you want to maximize? SA plus SC. FSA plus FSC. Because these are the things coming out of S, right? So that's what you want to maximize. How many? And of course, the rest of your equations are going to make sure that the flow is good. All right? Then what? Max that. Then? Right. So you have equations that say FSA less than or equal to 5, etc. FBT less than or equal to 3. Okay? So you have 9 equations, 9 variables, 9 equations. Of course, you are going to have FSA up to FBT are non-negative, right? Thank you. And finally, what do you have to do? Right. So you want to have 4 equations that say that F sub SA plus F plus CA must be equal to F sub AB plus F times AD plus, that's it, right? And that's it. Okay? Think about it. That's exactly what we want. We want non-negative numbers flows for every edge so that they satisfy inflow equals outflow, flow, Kirchhoff's first law, so to speak, and they satisfy the capacity constraints. That's all the constraints we have. Anything that satisfies all this is a flow. Now we want the maximum possible, which means the one that maximizes the sum of everything coming out of S, or if you wish, everything coming into T. Same thing. So you maximize these, subject to these 9 equations, subject to these 4 inequalities, subject to these 4 equations. Why 4? 1, 2, 3, 4 nodes, okay? One equation for every node. And you are done, okay? You do this, you download simplex, you press the button, and you get the result. Okay? Any questions? So we'll have a lot more to say about this problem. Okay, max flow problem, we're going to solve it with bare hands. Okay, no simplex. All right, but why? Because this was only the warm-up. Okay, to say okay, it can be solved by linear programming, but there is a very cute algorithm that you can use to solve it directly. All right, and this is what we're going to do next. But and in fact, this algorithm will show you the magic of duality, as this thing is called, how by solving it, you also get, as an extra bonus, valuable bonus, a proof that what you found is the best. Okay? Like happened before. Questions? The algebraic manipulation are going to, yeah, you are going to talk about it in great detail. The simplex algorithm, how you can, in other words, the simplex algorithm will take this data and will start doing algebraic manipulation to it, and then it will come up with the optimum solution. Okay? And we are going to see how simplex works in detail. But from now, for now, let's look into this as a graph theoretic problem, right? Like we looked at the minimum spanning tree and shortest paths, all right? And say, what kind of combinatorial algorithmic tricks can we do in order to solve it, all right? In fact, we'll do something slightly better and informed by simplex. We'll say, okay, suppose we gave it to simplex. What would simplex do, okay? That's a nice way to start. And if you think very hard about it, essentially, what simplex would do on this one is a very common sense algorithm. All right? So here is the algorithm. Start with all flows equal to 0. So what we're going to do is we're going to mimic simplex. What does simplex do? So what simplex does is the following. It starts with a simple, easily available, but a little ridiculous solution, right? So it says, suppose that all flows are 0. Any objection to that? No, except that it doesn't help me, all right? So, you know, but imagine that all flows are 0. It certainly satisfies all the constraints. So it's a feasible solution. Exactly like not producing anything was a feasible solution in the original problem that we talked about, the optimal production plan. With the 2 products and then with the 3 products. You start from saying, okay, suppose we don't produce anything. Now what do you do? Now you look around and you find the best way to go. Okay, what do you do in this case? Okay. Anybody has an idea? Remember, you want to find a slightly better flow. What would you do? Yeah. Right. But this would not be a feasible flow, would not be a feasible solution, would not be a solution that satisfies all constraints, okay? I want to keep solutions that satisfy all constraints. Do I make sense? I want to find a flow which is a little less ridiculous, less self-defeating than this one. So what can you do? Any ideas? What is a very simple improvement I can make to my all-zero flow? Sorry? Make everybody equal to 1. That won't work, right? Because this is 1, this is 1, this is 1, I have a problem. Okay, it does not satisfy the equation. Remember depth first search, okay? So, what can I do? Yeah? Right, right, okay, cool. So, I find any path from S to T. Suppose I find, I don't know, what do you want? Suppose I find this one, the upper path, and then I say, okay, what I want to do is I want to make this path to set it to something which will keep it real, a real flow, feasible. So what can I do? What is the largest amount I can push along the highest path, the high path? 3, right? So I find the shortest path, I find a path, and then I find the minimum capacity on this path. And I say, all right, got it. I'm going to send 3 here, 3 here, and 3 here. Right? Okay, so here is a cartoon of the algorithm, all right? We will have to be a little more careful and clever, all right? So, start with all flows 0, 0 flow, nothing's happening. And then repeat. Find a path, push as much as you can along this path, and repeat until there is no path, in which case you know you are done. Okay? Any questions? Sorry? So, immediate problem. When so we do the first step, then obviously we must change the graph a little, right? Because some of the information in the graph is not right anymore. The capacity of this is really 2, okay? Not 5, because 3 of its capacity has been used. The capacity of this is 2, not 5. The capacity of this is 0, okay? This edge doesn't exist anymore because I have filled it. So find a path in the residual network. What is a residual network? As the name implies, it is the network that tells me how much more incremental I can do given what I have done so far, okay? Basically, it's a version of the original network which reflects what changes I have made. For example, here is the residual network in this case. It's going to be right? And this is 7, right? Right. Okay, sorry, thanks. And now I can start again. I can run my algorithm. Find a path in the residual network. That's the residual network. Which path do you want to find? Maybe this one looks good now. Or maybe this one. Then the residual network will be like this. And, right, find a path. In the end, we are going to find the path that we wanted, okay? We are going to find the optimum flow. So it looks like there is one little catch, okay, that we have to discuss, all right? So imagine the following. Suppose that instead of this one, you have this network here. Okay? S and T, simple network, everything is 1. Okay? So you find a path, any path. How about this path? Sure. This becomes 0, this becomes 0. What is the optimum, what is the best flow in this network? Would you say 2, right? Everybody says that? Here's how I can get stuck after 1. Okay, I find this, I get this path, I find my residual network, it's this, and now there's no path. Okay? So I made a mistake, all right? I made a mistake somewhere in my algorithm. Somebody suggested shortest path. All right. Imagine that, this is my network, okay? Then what? Okay? I will find this path. So that's not a solution. We have to redefine what the residual network is, okay? The definition of a residual network has to be a little more sophisticated than we thought, okay? Slightly more sophisticated. In particular, let me tell you what you have to do. Instead of decreasing the capacity of everything, okay, from 5 to 2, from 5 to 2, and from 2 to 0, or from 3 to 0, we also have to add backward edges, okay? That says the following, that record the fact, okay? Get it, so try to get it. That record the fact that we have already pushed 3, and if it's necessary in order to get to the optimum, we may cancel it. We may push back 3. We have up to 3 units of flow to push back along this edge. Okay? So here, that will be reflected by this edge that says that we have made this commitment, so we can take it back if we want. And now the shortest path will be this one, and we'll be done. No, no. So the question is, will this converge or will it loop forever? It will converge, and we'll see why next time.